On part two of the study guide, we're going to start by simplifying rational expressions. So the first thing you want to do before you try to cancel anything out, you want to factor everything. The bottom is a difference of perfect squares, and you can write this in any order. The top is just a regular kind of factoring. So you want to find products of the 12 is the product, the 7 is the sum. So 4 and 3 are the numbers that are going to work out there. So if anything reduces or cancels out, however you want to say that, or simplifies is really what it is, you want to do that. So these two factors get eliminated. So what's left is x plus 4 over x minus 3. Notice how I'm not writing the parentheses this time. There's nothing wrong with. You can rewrite them if you want. They're understood to be there. The restrictions on the variables, though, since we cannot divide by 0, x cannot be 3, obviously. But also, even though it reduced out, x cannot be negative 3 either. So I'm going to just write that as one combined statement. You could write it as two separate statements, but just saying that x is not allowed to be either of these numbers will suffice. But this is your simplified expression. For number 17, part of it's already factored for us, so I'm just going to flip the second part, turn this division into multiplication. I just have to take the reciprocal of the second one. I don't flip the first one. But before I rewrite this, I notice that there's two negatives here. If I pull out a negative 1, the GCF is negative 1, and I write x plus 3, that allows these two factors here to simplify. So I'm going to do that. Now, be careful. These two do not reduce. You can't do anything with that. Like, they look very similar. They're conjugates, but you can't cancel those out at all. The x's, one on top, one on the bottom. Those reduce 2. Simplify out. So we get the only thing on the top now is just the 2x minus 1. And then the two things on the bottom are the x plus 4 and the 2x plus 1. And those I have to put in parentheses. You can put this in parentheses, but it's not required, even though it is understood if you wrote it like horizontal ways. And again, I encourage you, leave the denominator factor. Don't feel the obligation to, distribute and write this as some polynomial. It makes it easier to just see if anything reduces. So just leave it in this form, even though it wouldn't be wrong to write it as a standard polynomial. They ask us to state the restrictions. So obviously we can't have x equal to negative 4 or x equal to negative 1/2. Otherwise that would make these denominators 0. But also, even in the middle of the problem, x cannot be equal to negative 3, because even if somewhere in the middle of the problem you were dividing by 0 or potentially dividing by 0, you have to account for that. And also right here, even though this canceled out, you still have to account for that. So these are the restrictions that x cannot be, otherwise you divide by 0 and the universe explodes. But this is your simplified expression. Okay, for number 18, so first thing I'm going to do is I need common denominators because I'm adding two fractions. So I'm going to factor this denominator here. So this is x plus 3 times x minus 1. So now that I've factored that, I'll cross that out. And I can see that the common denominator is just these two factors. This second fraction has one of those factors, but it doesn't have the x minus 1. And so the common denominator, okay, is x plus 3 times x minus 1. I only have to write that once. No need to write it twice. And then we have x squared minus 1 minus, and I want to be careful here, I want to subtract all of this stuff. But before I do, there's some understood parentheses that are always there. And so I need to distribute this result. So this becomes x squared minus x, and then plus x, and then minus 1. These things cancel out right here. And so this becomes minus x squared minus 1. Here's where I said you got to be careful with subtraction. You got to distribute this subtraction here. So here I have x squared, and then that's a minus an x squared. So these two kind of cancel out here. And then this becomes, I have a negative 1 right here. And then I've got a positive 1 right here. So this becomes, this actually just cancels out, does that cancel out to 0? So yeah, my numerator just becomes 0 all over x plus 3 times x minus 1. Well, 0 over anything is just 0, so there's no need to even write the denominator because, for instance, 0 over 1 is 0, 0 over 7 is 0, so no need to even write a denominator. But I still should write my domain restrictions because they asked for it. So the restrictions are x cannot be obviously 1, x cannot be negative 3 because of this guy right here. So this is your answer, and these are the restrictions. For 19, once more, I'm adding fractions. The previous one I was subtracting fractions. So the same thing applies. You just don't have to be as concerned with distributing a negative here, which is nice. But you should still look for a common denominator. We don't have one, so start factoring all the denominators that exist here. This is a difference of perfect squares, so that means that this denominator needs the x plus 2. So we need to multiply the top and the bottom of this guy by x plus 2. So once I have my common denominator, which is just the x minus 2 and the x plus 2, I need to simplify my numerators and combine like terms. So this, we actually do multiply all of this out on the side. If I multiply these two binomials, the x plus 4 and the x plus 2, I did it using the rectangular method. You can do it any way you want. You get x squared plus 6x plus 8, but then I got to distribute an x to that, so you actually get x cubed plus 6x squared plus 8x. This thing right here I'm adding, so I don't have to worry about distributing negative, so it's plus x, and then it's a minus 1. The only like terms that I can combine are the plus 8x and this, which is essentially a 1x. So we get x cubed plus 6, x squared plus 9x minus 1 all over that common denominator. And of course, like I said, you always have the option. This is, if you want to, now that we see nothing really factors out, nothing cancels out, you're totally allowed to just write the denominator as x squared minus 4. If you want to simplify it, you can, but don't feel the pressure to do so. You don't have to do that. For the restrictions, we know that we can't divide by 0, so x cannot be 2. And x cannot be negative 2. So those are your restrictions. Now we're getting into solving rational equations. So you can still, use the method. This first one, I'm just going to get a common denominator here. And so I get 2x over 4 equals x plus 1 over 4. But notice that to get x by itself, I end up to cancel out these 4's. I end up multiplying by that common denominator. So from now on, so notice I end up multiplying by the LCD, the least common denominator anywhere, or really any common denominator. I'm just going to do that from the start every time. So we get 2x equals x plus 1. Solve for x by subtracting x on both sides. And so we get 1x is equal to 1, or just x equals to 1. And they say check your solution. So let's see if this works out. If x is 1, put 1 in place of x, equals 1 plus 1 over 4. Sure enough, 1/2 is equal to 2/4. So this does check out. I know this answer is right. For number 21, if I went through the trouble of actually finding the common denominator and setting up equivalent fractions, that's, it's kind of exhausting. So instead, I'm just going to multiply by the common denominator. Just seems to be, these have nothing in common. So I'm just going to multiply both sides by each of those denominators. So multiply the right side by, then multiply the left side by this, and you see this one cancels out on the left side, and the other one cancels out on the right side. So you end up getting 3 times 3x plus 2 on the left is equal to 4 times x minus 1 on the right. And another way of seeing this, in this particular instance, you could see them as proportions. You might see it as, oh, didn't you just cross multiply? And that's another way of seeing what I did. I don't want to lean on just seeing it as cross multiplying, because in the future we'll be multiplying by the least common denominator. But that's exactly why it works. So then we just have a regular equation stuff you solved in Algebra 1. This is 9x plus 6, be careful distributing, 4x minus 4 makes you distribute that 4 to that 1. And then just, move the stuff on put constants on one side, variables on the other. You end up getting 5x equals negative 10. If you divide by 5 on each side, you have x is equal to negative 2. Now, you can always check. There's no need to wonder if your answer is right. I think that x is negative 2. So everywhere I see an x, I'm going to plug in a negative 2. So on the left side, I get 3 over negative 3, which comes out to negative 1. On the right side, I get 4 over, let's see, this is negative 6 plus 2. Negative 6 plus 2 is negative 4. That also comes out to negative 1, so the answer checks out. I know for sure that I'm right. Another way to check this is graphically, but graphically, you'd have to graph these two things and find the intersection. So algebraically is just a better way to do it, but know that solving it by graphing and finding the intersection, just like every other kind of equation, is a legitimate strategy. For number 22, again, you could kind of do this. Let me do this one the proportional way. So let me just say this is 0 over 1. You could see this as 3x is equal to 0 times x plus 1 if you're going to solve it by cross multiplying. That works. But another way of saying it is like you really don't even need to bother with the common denominator because you could just see this 3x is equal to 0. So you get the obvious answer that x is equal to 0, and I'll check that. If I do, make sure that works and make sure it doesn't make the denominator equal to 0. 3 times 0 is 0. 0 plus 1 is 1. So let's see if that checks out. 0, another way of saying it is 0 over 1. You don't have to put the denominator. So 0 over 1 is equal to 0, and that checks out because 0 equals 0. For 23, once again, I want to find a common denominator, but instead of just doing that, let me look at this thing and factor that. So this is a difference of perfect squares. Notice how instead of multiplying each side by each thing, the common denominator, each of these has a piece of it. So if I multiply both sides by this common denominator, which is the x plus 1 and the x minus 1, since this whole thing is this whole thing, those cancel out because this is your LCD. But on the right side, when I multiply that, only one of the factors cancels out, namely the x plus 1. So we get 3 times x minus 1 on the left equals 1 times nothing because it just all canceled. Distribute this, or you could distribute and get, I'll actually work this two ways. You could distribute it, then add 3 on each side, and then simplify, you end up dividing by 3 on each side, and you get x is equal to 4/3. And of course, you should check that solution. That's a good idea to do that. I'm going to avoid checking it by hand. But let me show you another way we could have gone. Once we get to this step right here, let me branch off a different way. So I had 3 times x minus 1 equals 1. Instead of distributing, you could have actually divided by the 3, like so. And then you get x minus 1 is equal to 1/3. And if you add 1 on each side, if you add 1 to 1/3, you get 1 and 1/3, which is the same thing as 4/3. So you could write this way. You could write the answer as 1.3 repeating. You could write the answer as 1 and 1/3. All of these are the same value of x. Instead of checking it by hand, since all you're doing is really just calculating whenever you check by hand, let me just use a calculator. So I'm going to do 3 over x plus 1, but instead of x, I'm going to put 4/3. So and notice how I'm not going to put 1.3. That's a rounded value. It'll throw the answer off. When you're checking the answer, I highly suggest using the improper fraction. So let me do 3 over, let me do 4/3 plus 1. And so I get this crazy number. So it's very intimidating. But before I make a choice, before I give a verdict, let me check the right side. 1 over x squared minus 1, but by x squared, I mean 4/3. So let me do, put this in parentheses, 4/3. Take that, square it, and then subtract 1. And look at that, I get the same answer both times. Let me show you one other trick that I don't think I've showed you yet. If I take the 4/3, okay, I can actually store that in place of the variable x. And the cool thing about this is, even though it's a repeating decimal, it stores it to like really high accuracy. Then you can just type the actual expressions in there. So I can do 3 over x plus 1 And notice how I get the exact, I get this number. Oops, that is wrong. I did 3 times x plus 1 there. Let me try that again. So if I do 3 divided by x plus 1, you'll notice I get the same value, the 1.2857. I get the same thing I had before, and I can do the same thing for the other one. 1 over x squared minus 1. And let me fix that exponent, hit the wrong button there. And notice how we get the same answer that way. So you can, another cool way, you can store that value into x and just literally enter the expressions as you see them. You can also use alpha y equals to enter the expressions this way. So there's tons of ways to check that don't force you to actually check it by plugging it in by hand. Calculators are great for checking. Either of these is fine. 4/3, 1.3 repeating, 1 1/3 is the next number. All of those are different forms of the correct answer. For number 24, once again, if you just multiply by the least common denominator, now you can multiply each of them by all of the things. You might think your common denominator is 3x cubed, but actually 3x squared also works. But here's the thing, I'm going to do a lazy thing. I'm going to just multiply by 3 and x squared and x to each of these things. So even if you don't, I'm going to show you that even multiplying by not the least common denominator totally works out. So here, the thing that cancels out is the x squareds, but then the 3 and the x persists. So you get 6 times 3 times x. And then here, the 3 would cancel out with this 3, but the 1 still gets multiplied by the x and the x squared. And then here the x's would cancel out, and so this one still gets multiplied by the 3 and the x squared. Now, all of these, I didn't multiply by the least common denominator in this instance, but it would still work out if you want to do it this way, if you don't want to go through the trouble of finding the least common denominator. So we get 3x squared plus 1x cubed equals 18x. But notice how they all have an x. So I could just kind of factor an x out of everything and just get 3x plus 1x squared is equal to 18. Now we end up with a quadratic. So you can't, even though I have all the x's on one side and the numbers on the other, remember to solve a quadratic equation, you put this in standard form. X squared plus 3x. You want to move this 18 over to the side here. Get equals 0. And then you could solve this by factoring. I think I can factor this by doing x plus 6 and x minus 3 equals 0. So my solutions are x equal negative 6 and x equal positive 3 should be my answer. Well, what if you're not great at factoring? Well, let's use our old friend, the quadratic formula. The quadratic formula is negative b plus or minus square root of b squared plus minus 4ac all over 2a. So I go to quadratic formula, and my a, b, and c are, my a is 1, my b is positive 3, my c is negative 18, and you could solve the equation that way. You could, of course, use the quadratic formula by hand, but remember, calculators are good at calculating. Let them. The last way you could solve this, I'll do it this one time. You can solve this by graphing. Go into your calculator, into your y1, you could put the left side of the equation in y1, the right side in y2. Alternatively, you could also, move this to the other side and put 0 on one side and solve for your y-intercepts. That works. Either way you want to do it, graphically is, I usually love solving stuff graphically. It's great, but it's just a little harder to see solutions sometimes. So I can see one of the solutions. You see how they seem to intersect at positive 3? And maybe you don't see that. Let me go to second, calc, and go to intersect, option 5. And they seem to intersect pretty close to there. I'm going to hit enter 3 times. And look at that. The intersection, the x value is 3, which is one of the values we saw using the other two methods. I can't see that negative 6 at all graphically. Now, these two things seem to get close to each other. But in order for me to see that, I kind of have to go to zoom in, and I'd have to zoom in on these points that are way to the left, and it's really just pure luck. If I go to zoom in on this part right here, I only know to zoom in at negative 6 because I found those answers before, but otherwise it's really impossible for me to see that. But I can do second calc, intersect, hit enter 3 times, and you can get the negative 6, the x values are what's important as the solutions. So you can solve these graphically. It's the most time-consuming method I find, and it's the least clear method, but it can be done if you don't want to do it algebraically. One more way that works is you could solve it using a table, using guess and check, or you could scroll through. If you notice, if I go to my table and I set this to auto and go back to my table, if you notice, when x is 3, see how they agree with each other, but they don't agree with each other anywhere else. And the problem with this is you also still have to kind of know where to look. They also agree with each other at -6. I only need to look for 3 and -6 because I knew those were the solutions. But just kind of drudging through here and just kind of digging through and trying to find the answer, not the most efficient way to do it. So that's why I lean on the algebra. For number 25, this is the last rational equation we'll solve. You can see that the common denominator is just the combination of the two denominators that we have there. So I'm going to write this all out. So I'm going to multiply each piece of this by both denominators, right? And so here the x is reduced, here the x plus 2 cancels out, simplifies. So we get 1 times x plus 2, which is just x plus 2. Then we get x times x, which is x squared, equals 1 times all this. So that becomes x squared plus 2x. And you might think we'd have to use quadratic formula again. Actually, in this one, the x squareds conveniently just eliminate each other. So we get x plus 2 is equal to 2x. Subtract x on each side. And so we get 2 is equal to x, also known as x equals to 2. If you So I can check whether it's like true or false here by plugging it in this way using this test logic. This isn't something you need to be super familiar with, but it's not actually solving an equation. It's asking the question, hey, are these two equal? Notice these are not equal, so it's like the 0 is like a false, these are equal, the 1 is like a true. Either way you answer, this is your solution, x equals 2. For number 26, we're going to solve this first using rational expressions. Then I'm going to have a separate video where I work a lot of problems similar to this, the kind of word problems you're going to see. So we know that your neighbor can do a job in 4 hours. So the idea is they do 1/4 of that job each hour. So they completely seal 1/4 of the driveway in each hour. So that means after one, if we look at, let t represent the number of hours. So after 1 hour, for your neighbor, 1/4 of the job is done. After 2 hours, 2/4 of the job is done. After 3, 4 hours, 3/4 and 4/4, i.e. the whole job is done. Now, you don't know how long it takes you to do it, but you know that together you can do it in 2.3 hours. The important thing is that to get the rate at which you do it, you take the reciprocal of how long it takes you to complete the job. So the idea is that your neighbor, since it does 1/4 of the job each hour, if you do 1/4 times, let t represent the number of hours, you could also use x. That's how long it takes for that's how much of the job your neighbor completes in t hours. You don't know that what your rate is. That's what we're trying to figure out, but we know that 1 over whatever your rate is times t is going to be equal. We know that if we set this equal to 1, the job being complete, well, what does the t become? How is that useful? They give us 2.3 hours, but that tells us how long it takes for the job to be done with you two working together. But why did I write a 1 here? Well, the 1 is the entire job being done. So what's t? T is the time that it takes you guys working together. So this right here is the t value. So I know 1/4 times 2.3 plus 1 over, we don't know how long it takes you to do it by yourself, times 2.3 is going to be equal to 1. So we just have an actual application of adding and subtracting rational expressions. So this is 2.3 over 4 plus 2.3 over r equals 1. our common denominator is 4r, so we need to give this equation right here, we need to give this a couple of r's, we need to give this one a couple of 4's. So the common denominator, we have 2.3r plus 2.3 times 4 all over 4r is equal to 1. And just to be consistent, I know at this point I could actually like cross multiply if I need to, but the idea is I'm going to make the common denominator stretch all the way across the other side as well. I'm going to multiply the 4r by this over here, so I get 2.3r plus, let me just simplify this out. Actually, I'm not going to simplify it out. I'm just going to keep writing this, equals 4r, and then I'm going to solve this. So we get, if I subtract on both sides here, I'm going to get 2.3 times 4 is equal to 1.7r. And I'm just going to take that 1.7 and divide by that on both sides, and that will give me my answer of how long it takes me to do it solo. So run that in my calculator. Again, the reason why I leave this unsimplified because one, to avoid rounding errors, which won't be an issue here, but two, to see where the numbers come from so I can generally solve other equations like that really easily. So I get about 5.4 hours. So it'll take you about 5.4 hours to do it by yourself. Now, another thing you could have done, if you're familiar with the formula, you could use the A times B over A plus B, and that's the time it takes working together is 2.3. You could actually try solving it using this, knowing that it takes your friend by himself 4 hours. So you could do 4 times the B is how long it takes you over 4 plus B equals 2.3, and then you could cross multiply here. This is really 2.3 over 1. And so we have 2.3 times 4 plus b equals 1 times 4b. That's this right here. Again, I'm just cross multiplying like so. I'm doing this thing times this thing. And you get the same answer if you do it that way. But this requires knowing that formula, and you're applying it in a little different way. Instead of being given the individual rates, you're given one individual rate, and you're given a together rate. But you can still manipulate that formula to do it if you don't want to do it using rational functions. Another way to do it, of course, is guess and check, but that would just take a lot longer to get through. But there will be a separate video working a lot of problems similar to this one. For number 27, so let's think of a situation where you use inverse variation. In class, we talked about a pizza one, where if you have a finite number of pizza and you have more people at your party, that means that's less pizza for each person. But realistically, you would just, buy more pizza, or maybe like charge people. But let's think of a different scenario. Let's say you only have like one TV, right? And on that TV, you got like a little video game console. And the thing is, you can play like 4 players at a time on that video game console. Now, if you have 4 players at your party, then that means everyone can play the video game the whole time. Well, let's say you have 16 people at your party. Well, since there's only one video game console, that means you can only play a fourth as much. So to think of describe this as an inverse variation, this is the people at your party, and this is the time the fraction of time that you get to play. So if you have only 4 people at your party, you get to kind of always play the video games. If there's only 8 people at your party, that means that you'll have to take turns. You get to play like half the time. If there's 12 people at your party, you can only play still 4 people at a time. A third, 16, a fourth, etc., etc. So you might not want to invite 100 people if you have only one video game system, because the fraction of time that each person gets to play is going to be lower and lower. The idea is that as one column goes up, it causes the other column to go down, and this fraction, this would be the time that every one person gets to play, is equal to you only have one video game system divided by how many people you have. If you had 2 video game systems, you would just change this to a 2. If you had like 5 TVs and 5 video game systems with 4 people each, you could write it that way as well. And then, sorry, this would be These numbers actually would be 4 over that. So it's like this is how many people you can play at a time divided by how many people you have. And if you had 2 video game systems, this would be 8, and this one would be 12. And you can see that but the idea is that based on what I have right here, this is the proportion of time you get to spend on there. Inverse variation. For 28, really there's basically no difference when you're talking about simplifying rational expressions. Here's the only thing that's maybe slightly different. When you have a variable in the denominator, it means that there's going to be certain values of x where you're going to be dividing by 0. So you do have some restrictions. That's essentially the only difference. For 29, we're talking about when do we have vertical asymptotes. So for this one right here, you have a vertical asymptote at x equals -3. But if we wrote x plus 3 over, so for this first expression, at x equal -3 and x equal +5, these are both vertical asymptotes. But if we look at this second expression, here, this factor is going to cancel out. So for this one, you have a whole at x equal -3, whereas in the first one, you have an asymptote at x equal -3. Now, in both scenarios, you will have an asymptote at x equal 5. So if it cancels, you get a whole. If it doesn't cancel, you get an asymptote. For 30, if you want to write a function that has all 3 of those, really you could just look previously at one of the answers earlier in this study guide where it has all 3. So I would encourage you find the problem that had a vertical asymptote, a horizontal asymptote, and a whole, and you could just create your own. But the idea is if I want a vertical asymptote, I just have to divide by 0 somewhere. If I want a whole, I want to divide by 0 somewhere like right here, but I want it to cancel out with the numerator. And then the horizontal asymptote in this case, since the numerator and the denominator have different powers, the horizontal asymptote would be y equals 0. If I wanted to have a different horizontal asymptote other than that, what I could do is I can introduce another factor. Let's just introduce this. And here the horizontal asymptote would be 1 over 1. And let's say I want it to be 1/3. I could do like that. Now the horizontal asymptote would be 1 over 3. For 31, we're not asked to actually simplify this complex fraction, but I know I can't divide by 0. So x cannot be -4. And I know I can't divide by 0 here, so x cannot be 0. And those are the two denominators, but here's the thing. This is also kind of part of the denominator. It's the denominator of the whole fraction. So if you look at x squared minus 1, and you want to find out where that becomes 0, if you factor this thing, x plus 1 and x minus 1. So also, so not only -4 and 0, but -1 and +1 are all going to be restrictions on the variable x.